Hello everyone and welcome to my talk. I'm Mark Price from UMass Amherst and I'm representing the Human Robot Systems Lab led by Dr. Megan Huber and the UMass Integrative Locomotion Lab led by Dr. Wouter Hoogkamer. Special thanks to Banu as well for helping with these slides. So most of us at this conference don't need to be convinced that robotic exoskeletons are a promising technology, especially for gait assistance and rehab, but in order for us to be able to use it effectively, we need a better understanding of a few things. So we need to understand how human gait behavior responds to exoskeleton interventions in general, but more specifically, whether that response involves neural adaptation. And the reason we care about this is because it defines how the technology can really be used. So if you consider the difference between a mobility aid, which I use a wheelchair as an example here, versus actually using it as a rehab tool, with rehabilitation, you need neural adaptation for it to be useful if you're rehabilitating motor function that's been lost due to neurological causes like having a stroke. But you may not want neural adaptation if you're using it as a mobility aid because you could be causing someone to adapt to be dependent on the device to get around at all. So how do we know whether neural adaptation is happening? Well, we can look at some behavioral signatures, and this is from a split belt treadmill study, but it applies in general. You have some measure that has a baseline value that changes upon a perturbation. And what you see is that there's an initial response away from baseline, then an adaptation that happens over time while the perturbation is still being applied, and then when the perturbation is removed, because the brain has adapted, the motor control has been retuned for this new set of circumstances, that controller is still in effect when the external circumstances get reset back to normal. So you have an after effect where the behavior usually goes in the opposite direction of the initial perturbed response, and then that eventually washes out and you go back to normal. So if we're looking at other studies that have looked at hip exoskeletons in particular, we don't really see these signatures of adaptation. So in this case, we have a bilateral exoskeleton applying stiffness between the hip joints, and if you look at these plots at the bottom row, we either see a decrease in the relative range of motion and then immediately goes back with no jump in an after effect direction. This indicates that there's not really any neural change happening. But what if we want neural change because we're focused on rehab as opposed to a mobility aid? Well, we can look to other technologies that have achieved this effect for inspiration, and in our case we're looking at split belt treadmills. So with split belt treadmills, we see that we can get these behavioral signatures of adaptation by running belts under the feet at different speeds. But the critical point here is that it causes the person to walk asymmetrically, and they eventually correct that over time, or at least they move away from that initial response. So that caused us to ask the question, can we elicit a similar response by encouraging asymmetric steps with an exoskeleton? So our study here was we were testing whether applying unilateral stiffness by the hip exoskeleton would elicit neural adaptation by encouraging asymmetry. So our procedure was we had 5 participants. We had them wear the exoskeleton that's got a Defy actuator, 6:1 gear ratio on the right side. There's nothing on the left side. We collected motion captures, so we put markers on the lower limb segments as well as a separate marker set on the exoskeleton so that we could measure its positions in space separately from the joint angles so that we could account for any relative motion between them. And we had them walk for 5 minutes with the controller off, then suddenly the controller turns on, and they walk for 10 minutes with an asymmetric stiffness being applied on one side, and then an additional 5 minutes for the washout period where the controller was off. We did see signatures of neural adaptation when we did this. So on the top, you can see our mean values and our standard deviations and our statistical comparisons. And then the bottom row, you can see the individual responses of all the 5 participants. So it's pretty consistent across the board, at least for this measure, which is the hip range of motion. And so what we saw was that when we initially applied the controller, then the range of motion initially decreased on the right side, as we would expect, and then we saw a complementary increase on the left side. And then that right side range of motion started to increase again. It never quite reached the baseline value, but then when we removed the stiffness, we saw an after effect as well, where the right hip range of motion actually increased above baseline and then went back to normal. If we look at step length, so this is just the distance between the feet at heel strike, and we saw a similar effect, a little bit less obvious, but we did see a change at least at the initial perturbation, and that then appeared to return to baseline, but we did not see a significant after effect for this one. We also looked at step time and saw no significant change. While we did see some spatial changes, some signatures of adaptation there, we didn't see anything for the temporal measures. So our discussion points here, we see some signs of neural adaptation. However, we can't strongly conclude that these are driven by the nervous system for a few reasons. One, they're somewhat inconsistent across different parameters. So we're comparing hip range of motion versus step length. Range of motion, we saw all the classic signs, but step length, there's no after effect. This could be due to the fact that maybe our perturbation was just not asymmetric enough, and we just didn't have a large enough effect size to have that significance be observable. On the other hand, perhaps we're just seeing the passive dynamics of the walking person in this new set of constraints converging to a new solution over time, and the brain might have absolutely nothing to do with it. One final thing is that subjects preferred to walk with asymmetry while the stiffness was being applied, even though the hip range of motion became less asymmetrical. It did not get driven to zero, which is what we usually associate with adaptation driven by what we'd call error augmentation training, where you want to drive what the brain sees as an error to zero. It did not do that, which means it is not the only thing that is driving the motor control change there. Thank you for your attention, and feel free to contact me or anyone from our lab group at this conference, and I appreciate your time. Thank you.